Okay. Well, thank you everybody for showing up. Welcome to the February 11th edition of our working group and our two mini talks. I'd like to remind people that this meeting is live streamed and recorded and will be made available for public use after the meeting is over. As usual, introduce myself, James Glazier, Indiana University, Reinhard Abenbacher in Florida, although sitting in Connecticut today, and our team, Jim Sluka and Bruce Shapiro, everyone hears from quite a bit. Remind you that we have a Slack channel, which you're free to use. If you need information on how to get to it or use it, please contact us. We also have the IMAG MSM wiki page that always needs love, so your contributions to that would be much appreciated. Again, if you need access, let us know. I was asked by a group at NSF to say that there is an NSF symposium on predictive intelligence for pandemic prevention. While much of this is focused on epidemiological modeling, it does have an in-host component to it. I would encourage people to check out the website for that. They're having a meeting, open meeting on February 22nd and 23rd, and they would love to have participation from our working group members. So I would encourage people to check that out and see if it's of interest to you. We have a number of very good upcoming mini symposia, mini presentations scheduled. February 18th, we have Tomas Helikar, who does extremely interesting modeling of gene, especially gene regulatory networks, and also has done a lot of interesting work on outreach. We heard a little bit about some of his work a few weeks ago in the presentation from the joint French Luxembourgese presentation. You have Marie Ferguson, and then the following week we'll have Rita de Almeida from Brazil talking about analytic methods for trying to quantify gene expression in the context of SARS-CoV-1 and CoV-2, and Jim Fetter talking about modeling viral replication dynamics. As usual, we would love to have suggestions for speakers and volunteers for speakers as well. So with that, I don't want to take more time away from our speakers. Do we have Ruchira on the call?
Yes.
Okay, I will turn over the screen share to you. And if you can, as usual, I'll remind people that please try to keep things to 15 minutes so that we have time for some questions.
All right, now I'm unmute, hopefully. Everyone can see? Great. All right, so this is an invitation to approximate Bayesian computation for complex stochastic simulations. And since there's a very varied backgrounds among the people in this group, some of what I say will be familiar to many of you, but I hope that this is enough to get you an idea of what is the idea behind approximate Bayesian computation and to get you interested enough to look into it for your own simulations. So this being the modeling group, many of us are doing simulations. So the general scenario is we start with a specific model. We might be able to do model selection, so we could start with multiple different models, but for now I'll just start with one specific model, and we fix a vector of parameters, theta, and we perform a simulation run. We let the model variables interact with each other. There might be evolution over time or over space of the state of the variables. and then we analyze the outcome variables of interest. So that might be a vector of variables x, and we might have different purposes in running this simulation. We might want to evaluate the mechanistic explanation. Our model might be embodying a mechanistic explanation of a phenomenon, or we might be wanting to make predictions. So the final outcome variables may be the things that we are trying to predict. So that may be the useful question that we're trying to answer with these simulation. So now, with stochastic simulation, we're introducing that there's some uncertainty in our model. So this could be because there are uncertain initial conditions. This could be because there's measurement error of the state variables, or the variables that are the independent variables in our model, or the observations also. Then another level is that there could be uncertainty in the parameter values themselves, and this is actually the scenario that we're particularly going to be interested in for ABC. And there could be inherent randomness. Now, what do I mean by that? So, in general, quantum physics tells us that physical reality in general is inherently random. However, there's a large class of models that we find to be computationally tractable and cognitively appealing, and that are useful, that are deterministic. So determinism is an approximation. And so when we talked about simulation in the first slide, we could have been talking about a deterministic approximation. But in some cases, depending on the questions that the particular questions that we're addressing with our model, it may be that for those three criteria, it's actually easier. It may be more tractable, or it may be simpler to just use a random model. It may not be random down to the level of quantum physics, which may not be applicable. But even the approximation itself, it may be easier to use a random approximation of reality rather than a deterministic approximation. So at that point, our simulation becomes stochastic. So we need to use random variables in our model, and then we need to perform many different simulation runs. So we're sampling a space of many different simulation paths according to the different draws of the random variables. And then we need to analyze a distribution of the outcome random variables x. So we might want to characterize the range. For instance, if we have a vector of variables, we might find that certain states of different variables never occur together. That would be one characterization of the range. So initially, like 20 or 30 years ago, in terms of simulation, one would just play with the simulations and find interesting things. However, in order to use this rigorously, we want to actually estimate statistical properties like the expectation and other moments of these random variables. So in order to explain what we're doing, I'll just give an example which is in a simpler scenario than we just described. So this is Monte Carlo integration. So we have one random variable, capital X, with a probability density function, f of x, and we're interested in the expectation of a function g of x. So to get that exact expectation, the expression is that we integrate the function with respect to the probability density function, and then we get the expectation of g of x. So this integral, as it is, may not be tractable analytically. So we can do this integration by simulating realizations. So we can have n different realizations of that same random variable, one single random variable x. And so we're generating random quantities from that distribution with the probability density function f of x. And then we can approximate the integral by saying that the expectation of g of x is approximately the mean of these g of xi's. And so in this expression, we didn't have anymore the probability density function. It appears implicitly because we drew these probabilities, these variables from that probability density function. We simulated that probability density function. That's the basic scenario, and of course we're doing this multidimensionally. So a way of, now what happened here? That's not what I wanted to do. Oh, yes. So a way of doing this is with rejection sampling. How do I get back? All right. Okay, I'll just leave it like this. Okay, so we want to simulate this probability density function f of x, and in general, this density function could be quite complicated. And so in terms of generating random variables, we may not be able to, we may not know intrinsically how to generate that probability density function directly. So this is where sampling comes in. And so the example that I'll give is of rejection sampling, which is going to be important for ABC. So this is an example where we know how to generate a random variable with a uniform distribution. So suppose that the probability density function that we want to simulate, f of x, has support on an interval, AB, and we know that, and this interval, the values, the range of this probability density function is no more than m, some maximum, the upper bound of that range. So then we can draw the random variable x from a uniform distribution that is bounded on that same variable, that same support, AB. And at the same time, we can draw another random variable y, which is in this support of f of x, so from 0 to m. And so then we can evaluate f of capital X, our random draw, and then check whether y is less than that random draw. Y is less than f of the random draw. So this will then only, if this is accepted, if this equality holds, then we will accept our random draw as one of the random draws in our total sample, and otherwise we're just going to reject it and try again. So then there's some, it's a theorem that can be proved that the accepted draws will be distributed according to that probability density function f of x that we wanted. So it's a kind of a technique for simulating any probability density function, given that we know how to simulate random draws from a uniform probability density function. So now we had, that was an explanation of the basic idea between Monte Carlo, and generally in Monte Carlo integration that we just described, we were dealing with statistically independent samples. Now instead we want to deal with stochastic processes, and a Markov chain is a kind of a stochastic process that has the Markov property. So future states are independent of past states given present states. So it has a, so it's a conditional independence, not the full statistical independence. We have a memory of one. So if we have discrete times then we just need to know the previous state in order to get to the next state. So for a Markov chain, we have an initial distribution, pi naught, and we have a transition matrix, P of x given y. Now this is a shorthand that, given the present state y, what is the probability that the next state is x? So again, this is future states are given the present state, and we only need the present state. We don't need any past states. If the Markov chain is reversible, which means that, so you can think of this is transition from y to x, and then there's also transitions from x to y. It's reversible, so we can get between any of these two states symmetrically. This is the equation. Then this Markov chain has a stationary distribution pi. And what we want is to sample from the stationary distribution. So in Markov chain Monte Carlo, we could have multiple cold starts. So those are the initial distributions, because depending on our sampling, it may be that certain initial points may not necessarily get to the full stationary distribution. Some areas of the state space may be inaccessible. So we have multiple cold starts. Then we execute this Markov chain, which is a random walk according to this stochastic process. So this is a burn-in. And then we sample from the stationary distribution. And one key issue is the mixing time. So the mixing time means that we have run this Markov chain long enough to get to the stationary distribution. And so that we will see that it has converged, and that the distribution that we're seeing is the same over subsequent runs. Then we'll realize that it has converged. Now, in general, so in approximate Bayesian computation, we have the word Bayesian. So this is from the Bayesian scenario. I had mentioned that one reason why we're doing stochastic simulations is that we may be uncertain about the parameter values themselves. So we can make inferences about the parameter values. Is that something in the chat? All right. Yes. Yeah, I have just a couple slides to go. So we can make inferences about the parameter values by starting from data. So we're doing the situation that I had described. We were going forward, simulating from, given the parameter values, then what are the outcomes? So the distribution gave us the joint distribution of the outcome variables and the parameter vectors. So then we could factorize this distribution in terms of a probability of parameters and a probability of the outcomes given the parameters. And so then with this factorization, this factor is the prior probability of the parameters, and this factor is the likelihood of the outcomes given those parameters. And this is what we find by doing many, many simulation runs in this Monte Carlo simulation. So we can invert this using Bayes' rule, and then we can find the posterior distribution, the probability of the parameters given the outcomes. So we may have data where we've observed the outcomes, and then we want to know what parameters can we expect from that data, so that we can perhaps use those same parameters to analyze new data. Now, a problem with this general idea is that computing the likelihood is often intractable. So in my talk title, I talked about complex stochastic simulations. Actually, any simulation where the likelihood is intractable, we could call complex. So approximate Bayesian computation is a likelihood-free method where we don't have to compute the likelihood in order to infer the parameters. So there's a very nice summary of the idea from the Handbook of Approximate Bayesian Computation that came out in 2018. Numerical evaluation of the likelihood function is replaced with an assessment of how likely it is the model could have produced the observed data based on simulating pseudodata from the model and comparing it to the observed data. So I'll just very, very briefly say the basic steps of approximate Bayesian computation. So we have a sampling density G of the parameters. So that's from the prior. And we generate a set of a parameter vector, theta I. And then we generate a simulation run. So from this generative model, we have y is simulated according to the probability of y given those parameters. So this step, it can be our complex simulation. So it's written in one line here, but it can be, you know, an arbitrarily complex computer code, and there are methods for dealing with that. And then we compute a summary statistic, S, which is a function of y. And then we accept this parameter vector with a probability that's proportional to the distance of S from the observed summary statistic. So this is the key thing, the summary statistic. So we don't require that our simulation has to exactly give the outcome that we observed, the data that we observed. So that would be strict rejection sampling, that unless it gives exactly the summary statistic that is observed, we would reject it. And that would take, in practice, that would take forever. We would not get to convergence, because very few of our simulation runs would actually have exactly those values. However, now to be technically correct, we would have sufficient statistics. We would have statistics that are sufficient to say that it is from the actual likelihood. Even those may be too much. So the summary statistic is a computable, tractable set of statistics that we can measure from our data, and that it's balancing that it's tractable to get something close to that. At the same time, we're having enough samples that are accepted. So once we do this acceptance scheme, then the result is a distribution of parameter vectors. And then now that we have this distribution, then we can say that the data support various hypotheses, or that they're within a certain regime of the parameter vectors, and we can characterize the data. And so this has been approximate Bayesian computation has already been applied in a variety of fields. It was first created for the field of population genetics. So with these, there were aggregate populations, and there were various characteristics of the populations. It's also been, so I've put a sampling here which are perhaps relevant to this group specifically. It's been applied in ecology, in host parasite systems, in infectious disease dynamics, in HIV contact tracing, and pathogen transmission. And this one I want to highlight, colorectal cancer development. This is where I first encountered it. So this I think is close to our physiological models. So there's actual complex models that include different crypts in the colorectal. They're the pre-tumor and tumorous crypts, cancerous crypts. And so this is a case where we have this very complex stochastic simulation, and we're able to rigorously make inferences using ABC. So this is Sotorova and Tavare,
So
and then
I,
subsequent
I'm,
colleagues.
I'm sorry, we're going to have to wrap up here.
Yes, this is in fact the last slide. So I can give further references, and I hope that people can ask me
Great.
questions about further references for this topic.
Great, thank you. I appreciate your patience with the very short format. So we're going to hold questions. Everyone has your contact information. We'll hold questions till the end of the meeting. And thank you, appreciate that. And again, I appreciate everyone's patience with the very short format that we have to put up with here. Appreciate it.